All right, Steph, I think we're ready to start.
Great. Hello, and welcome to today's webinar, Create an Engaging CS Program with TETRIX Virtual Robotics. Thank you for taking time out and being here. Just a few housekeeping items before we jump in. We'll be running a live question and answer session towards the end of the webinar. Please feel free to use the chat feature on your participant panel and pop in any questions you may have in there, and we'll address them when the time comes. Also, if you miss any part of the content presented today, we'll send all registrants the on-demand recording as soon as it's available. We'll also be delivering certificates of attendance to all of our attendees today. Please be sure to turn those in for professional development credit if you're able to. Also, we'll email both the certificate of attendance and the recorded session using the address you provided during the registration process. My name is Steph Forbes. I currently fill a development leadership role with Pitsco Education. With me today is a colleague of mine that I am pleased to introduce. Aaron Locke is a curriculum specialist with Pitsco Education. Physics, family, and faith are the three F's that define Aaron's life. With a degree in physics from Pittsburgh State University, Aaron has always been drawn to how things work. Wanting to pass on his ambition led him to Pitsco Education, where for the past 16 years, Aaron has worked as a curriculum specialist, writing hands-on curriculum and activities. Before we get started with today's webinar, I'd like to share an introduction to the sponsoring organization, Pitsco Education. Pitsco is a leader in future-ready learning fundamentally rooted in STEM. For more than 50 years, we've offered a comprehensive range of scalable, hands-on resources and curriculum. We help educators create learning environments that address all learning styles and help all students find success while solving problems, being creative, articulating ideas, and thinking with their hands. It's our goal to make it easy for schools to bring materials to the classroom to create lifelong learners, successful professionals, and engaged citizens. We promise to remove barriers, to bring cutting-edge technology into the classroom, and to help teachers find new, relevant ways to do what they do best. Pitsco is the creator of the TETRIX Robotics building system. TETRIX Robotics is a metal building system that can be used both in the classroom and for competitions such as First Tech Challenge and Urban Search and Rescue. With TETRIX Robotics, middle and high school students design, build, and program robots with a purpose, learning to problem solve, test ideas, and develop perseverance along the way. Today, we'll be sharing about TETRIX Virtual Robotics, also known as TETRIX VR. The TETRIX VR simulation software provides an easy entry point for students to learn and practice computer science skills. TETRIX VR also provides educators with the curriculum and easy-to-use tools and all the resources needed to run a successful blended coding and robotics program. We'll discuss an overview of the program, the benefits of adding digital physical coding and robotics experiences to your computer science class, and the flexible ways it can be implemented. We'll show an in-depth look of the platform and demonstrate how students can seamlessly move their code from the virtual world to a physical robot using the Arduino IDE. Let's jump in. TETRIX Virtual Robotics is our coding and robotics solution that has been optimized for blended learning. TETRIX VR is 100% web-based and can be implemented in a coding classroom independently or through a blended digital physical experience with the TETRIX Max hardware. When used with the TETRIX Max robotics building system, TETRIX VR is one of the few solutions that gives learners the option to code virtually and then test their code on an actual robot. More and more technology is making its way into our homes. Today's students will not only need to understand how to use these technologies, but also how these technologies work. TETRIX VR brings real-world STEM concepts to life while making coding immersive, accessible, and fun for students. Through this program, students use the simulation software to code virtual robots. Students will learn how to write and debug code through real-world relatable scenarios. Students learn about robots that they might encounter in their lives, such as robots that mow the lawn or keeps their home safe. Even if a student hasn't mowed a lawn, they can understand why it could be useful. Students will also learn how robots work and how the code they write control a robot and how robots interact with their environment, whether in the digital or physical world. Students will also learn about the engineering design process.
So, Steph, with this blended learning combination, the digital and the physical, students will explore these concepts with a higher depth of knowledge than if they're coding just online or just working with the physical robot alone. So Norman Webb developed his depth of knowledge scale, sometimes known as DOK, and it gives us a common frame of reference to use when we're talking about how students engage with content and that kind of thing. So DOK helps us understand the rigor or the cognitive demand that's required by students to complete an assignment or a task. So Webb identified 4 different DOK levels that increase in complexity, in the complexity of thought that's required. So just to run through a few examples, as students work through the TETRIX VR system, here's the way it would work. So first, they'll learn just the basic coding, which serves as the foundation for their learning. So as an example, students might learn about concepts like pseudocode and algorithms, different programming structures, that kind of thing, troubleshooting. That's the level 1 stuff. That's the recall, just the knowledge acquisition. Then next, students are going to bring that knowledge to real life as they apply it, apply that coding knowledge and those concepts that they've learned in the digital environment in a hands-on way with the physical robot, where they test their written code. And then the third step, students will then need to analyze their work on the real robot to determine if the physical robot is completing the task that it was designed to do. And if not, they have to troubleshoot the problem and fix the problem. So in the real world, it always brings challenges that aren't accounted for in the simulation environment. And then lastly, every activity culminates with a challenge. So to solve that challenge, students are given criteria and constraints that they must follow. Students create new programs to solve these challenges by using coding concepts and skills that they've already mastered. And so those are the 4 levels, and it increases in complexity. And we walk students through those 4 different levels. So the TVR software also introduces students to syntax coding on a basic level. There's no prior experience needed or required. It allows them to progress their knowledge over time. So we start them at that level 1 DOK and then build them up from there. But it's not just about hard facts and knowledge. It's not just about that level 1 stuff. TVR is also about skill building. And so as they work through the programs, students will develop an array of computer science skills. You can see just a few of those listed on the screen there. But they'll develop skills like computational thinking, systems thinking, and data analysis, just to name a few. And so speaking of skills, many of the computer science skills that students are developing are aligned with the CSTA practices, that's Computer Science Teachers Association. So throughout this presentation, you're going to see how these practices are embedded into the program, and you can see those practices listed there as well.
As students work through the activities, they'll practice critical 21st century skills. Students learn to work through the problem-solving process, and they develop grit and determination as they gain a greater understanding of why it's important to persevere as they work to achieve their desired outcomes. When moving from independent work in the digital environment to collaborative work with the physical robot, students learn how to work together, listen to each other, and resolve conflicts. These are skills that all students can benefit from, no matter their future career paths. Plus, as you know, working in groups enables students to better understand and explore differing perspectives, and can also help them in establishing roles and responsibilities based on their skill set. One student might oversee monitoring the code on the screen, while another student might oversee monitoring the physical robot. Another student might take notes on the performance of the robot so that they can make adjustments if needed.
Another aspect of the STEM center type of learning that we've been talking about with TETRIX VR is that students work through the engineering design process as they go. When students are working through the activities and tasks, we're going to see those here in a little bit, they're iterating and problem solving. They're refining their code, just like real engineers do, as they're using simulation for both the virtual and the physical robot. So for example, when facing a problem, an engineer wouldn't immediately jump into building a solution as soon as the problem's been identified. Instead, an engineer would break that problem down into smaller parts, smaller chunks. And then they'd go through some kind of brainstorming process to identify possible solutions. The engineer might write out a step-by-step process to address the problem in everyday language. We call that pseudocode. And then when a viable solution is identified, an engineer might work with a simulation to test their solution before building a prototype. You know, they don't want to just jump right into using resources and time and all of that to build a prototype on something that might not be viable. And so the simulation really helps with that. So if the simulation shows that it has merit, then they would continue on with the next step, which would be prototyping. Otherwise, it's back to the drawing board to come up with another idea. Well, TETRIX VR works in the same way. Students are presented with a real-world problem, such as a dog walking robot. And then the problem is decomposed into smaller problems that we call tasks. As students work through those tasks, they'll first write and test their code virtually and use it in the virtual simulated environment. And then as their code has proved successful in the simulation, then they'll have access to a physical robot where they can transfer their code and test it in the real world. The simulation provides students a great way to see if their solutions have merit. So when students move their code from the simulated environment to the real world, then they're building their computer science understanding and skills as they troubleshoot and refine their code. So we all know that in the ideal world, things always work, but in the real world, there's all kinds of factors that can affect it. So their code might work perfectly on the computer, but when we move it over to the real robot, there are going to be other things that affect it. So it's usually far from ideal. So the factors like the performance of the robot is affected by the friction between the wheels and the surface that the robot's driving on. Maybe it's affected by the movement of the servo. It doesn't have the same range of motion, or battery life. The battery life can really impact a real robot, wear and tear on hardware, that kind of thing. So although simulations try to account for some of these factors, it's important for students to keep in mind that physical robots won't always perform exactly the same as the virtual robots. So the ability for students to work both in a simulated environment and then translate that to an actual robot is something that makes TETRIX VR stand out from other robotic simulators that are out there in the market. So while we're talking about learning outcomes, let's also talk a little bit about some of the activities that are included with TETRIX VR. There are 15 real-world activities for learners to work through, each featuring step-by-step coding instructions. Every activity includes a series of progressive tasks that concludes with an open-ended challenge. Remember, we're working through those DOK levels. So the activities are broken down into 3 units. Activities 1 through 5 is unit 1, and these feature an assistive robots theme. These are robots that help older adults and people who are disabled. And during these activities, students are introduced to the controller, the DC motors, servos, hardware, sensors, those parts of the robot. And then activity 6 is where students are going to move away from the computer, and they're actually going to go build the physical robot. So there's no digital component to that. We're going to just collaborate as we group together, work as a team, and build some of those collaboration skills to build the physical robot. We call it the TaskBot. It's a generic robot that serves lots of different purposes. Unit 2 is activities 7 through 10, and these feature a domestic robots theme. So these are mobile robots that do chores for us around the house. Steph mentioned mowing the grass, might be vacuuming the floor. We're going to look at walking the dog here in a little bit. So during these activities, students will use systems thinking and algorithms as they code their robot precisely where to go, how to navigate the robot. And then finally, the last unit, activities 11 through 15, are themed around safety and security. These are robots that utilize sensors to monitor and patrol homes and businesses, keep us safe. So using the TaskBot sensors, he comes equipped with a couple sensors. Students explore more advanced programming concepts such as conditional structures and nested loops, functions, those type of things.
All in all, there's up to 22.5 hours of classroom content, depending on whether your class utilizes a digital experience on its own or blends the digital and physical robotics experience together. Because the activities have been developed so no prior coding experience is needed, educators can focus on managing the classroom and facilitating student learning outcomes. Each activity has a teacher lesson plan that includes a lesson overview, real-world connections, learning objectives, coding concepts, a pacing guide, CSTA standards correlation, tasks, goals, teaching points, discussion questions, and sample code. You'll see an example of this during the demonstration platform and later in the presentation. As students complete each task in the platform, we encourage you to engage the class with guided discussion and review. The included lesson plans and teacher notes provide content to help with these discussions. Some of the discussion questions focus on ethical, social, and economical issues related to the robots, so that students can discuss how these robots impact our society. This software meets students where they're at and is suitable for students of all backgrounds. Students can work at their own pace and receive real-time feedback on their work as they progress. So now let's jump into the platform.
All right, so I'm going to go ahead and share my screen. We're going to show a little bit of the TVR system.
So Aaron, while you're getting that teed up, what devices does TETRIX VR work on?
Okay, so TETRIX VR is a web-based application, so it works on any device that has internet access. So Chromebooks, Macs, PCs, tablets. You could even use your phone if you wanted to. It's not recommended because just typing code, syntax code with a phone keyboard is not probably ideal, but you could if you wanted to.
So what if I'm using the digital and physical experience? Does that change what devices I can use?
It does a little bit. You're going to need a device that has a USB port, and that's mainly for transferring the code from the robot or from the computer to the robot. We use a USB cable to do that. So you'll need a USB adapter or a USB cord to do that. So a lot of tablets have those now. Chromebooks, of course, have those.
Great. Okay, so now that we know about device, does browser matter?
The browser doesn't matter a whole lot. It works best probably in Chrome or Firefox, Safari, kind of your main browsers. Those are the ones we would recommend. Chrome's probably the most popular. But yeah, if you stick to the main browsers, you'll be just fine.
Okay, great. So now I see you've launched can you tell me a little bit about what we're looking at?
Yeah, so we've gone ahead, we're logged into the system here, and we're looking at what we call the dashboard. It'll look similar for students and for teachers. The one difference will be the different menu options you have over here on the left. From here, you can access different courses. You can access your class and those kind of things. So this is the login screen, gives you access to everywhere where you need to go.
All right, so I'm a new teacher. I'm logged in. I looked at the dashboard. Now I need to start building my classrooms. Can you show me how we do that?
Yeah, so as a teacher, you'll have access to this My Class section. Students won't have access to that, but we'll jump over to that. And then across the top, you'll see different parts. You've got different tabs here across the top: My Classroom, Student Analytics, Educator Resources, so forth. So when you first log in, we're in the My Classroom section, and you can see our different classrooms that are listed here. And from here, you can access, you can manage the classroom, you can look at student analytics, you can actually sync a classroom with Google Classroom. So if you're using Google Classroom at your school, you can create your classroom and manage it through Google Classrooms. That's super easy to do if you'd rather do it that way than use the system. So
what if I don't? What if I'm not using Google Classroom? How do I create a classroom?
Yeah, so to create a classroom, we're first just going to click the Add Classroom button. You can select a grade, give it a name, put your school in, and create classroom. It's that easy. Once you've created a classroom, then you can go down here, you can manage your classroom. Once you manage your classroom, probably the first thing you're going to want to do is add students to your classroom once it's created. So there are 3 different ways you can do that. You can see those here. The red way is if your students already have a TVR account, then they've already got login and all of that. You can just send them a class code and that will add them to your class. That's usually not the case. Usually students that are starting TVR, they're brand new to the platform. And so you're going to need to either add students manually or auto-generate the students. Those are the blue and green options. So if we're going to add students manually, you can do that in 2 ways. You can use a CSV, that's what it is, CSV file, and just upload it using Excel or whatever. And we have instructions on how to do that. You can also add them manually one at a time. So you're just going to fill out these fields and add students. You can, as you fill out those fields, you can add to the list here. But it's important to note here that you'll notice the first name and the last name are optional. Those are for security reasons at your school. If you're pretty tight on security, which is great, really safe for the students, you do not have to put their first and last names in. All they really need is a username, which can be an email address, username or email, and then a password to log in with.
Great. So once I have my classroom built, what information can I see?
So we're going to jump into a classroom here. We'll go ahead and we'll, oh, I'm in the wrong place.
So what are those numbers next to the student name?
Yeah, let's talk about that for a minute. So I can look, just glancing here through my class, I can see the number of tasks that they completed. Remember, we talked about how the content was organized to units, then activities, and then tasks. So the tasks are the number of tasks that have been completed, and this just gives me a good look at where my students are. If one is way ahead, I know, oh, he's really progressing through this, and if one is way behind, I can work with that student to help get them caught up. You can also reset a student's password here if they forget it, and you can unenroll them from the class here as well.
Great. So I can gauge and see how students are pacing. Is there any other information or way to kind of track how students are progressing?
We can. So we're going to jump over to the Student Analytics tab and look at that. And so I'm going to select my class here. That loads. There are two types of analytics we can look at. We can look at progress data, and we can look at performance data. And so we're looking at activity 1 here, and here's my classroom. And I can look down my list of students here, and I can see exactly where they are. So the blue indicator shows me exactly what task they're on. So you can see for activity 1, we've got 6 tasks that students will be completing. Blue is what they're on. Green is what they've completed. Yellow, if I've got yellow, it's telling me that a student had trouble with that one, and I progressed them past that. And then, so they haven't completed that one. They've worked on it. They haven't completed it yet. So yellow are places where you might need to get involved as the teacher and go see what's going on. What are they not understanding? That kind of thing. If a student does get stuck and you just don't have time to work with them and help them troubleshoot their code, you can always move them on so that they can continue to work, and then you can go back and address them when you've got time as a student or as a teacher.
Great. So is there any other way that I can kind of track how students are progressing or see kind of an assessment tool?
Yeah, so let's jump in. We'll look at Garrett here. So we're going to jump in. We're going to look at his task 3 content here. Yeah, there we go. So once I jump into the task for a particular student, I can see the number of attempts they've tried at that task. I can click this button, and there is his code right there for that task. I can compare that to the solution code. And so we always provide solution code that works to complete the task. And I can walk him through if he's having trouble. I can walk him through just comparing side by side. I can expand this. Sometimes the window, especially on a small screen, is it doesn't make the code look great. So you can always expand the code. It makes it a little bit easier to compare, but you can look at it side by side. Okay, here's what Garrett's doing. Here's what the solution code is. What's the difference? So yeah, really helpful to be able to assess their progress, determine what they're getting, what they're understanding, and what they're not understanding.
Great. So now I've seen how I can assess students. What about the types of resources that are available to a teacher?
Yep. So we're going to go to Educator Resources up here. And from here, my course is the Virtual Prism Programming Guide. That's our introductory course for using this robot and TVR. From here, you can see the different PDF documents that we provide to support you as the teacher. And so Getting Started documents has different implementation ideas in the classroom. The standards alignment to CSTA are there. There is a document just for solution code. So you can print that out, and then you can, as you're working with students, walking around the classroom, facilitating, you can compare their code to the solution code. You have that available. TETRIX Prism Library Functions is just kind of a cheat sheet on the syntax of the different TETRIX commands and functions that are required to run the robot. And then similar, the Arduino IDE reference guide is the same thing. So one thing we didn't mention earlier is that TETRIX robots are programmed with the Arduino IDE. It uses the Arduino C code, C+ code. So we provide that Arduino reference guide for you to, especially if you're not an expert coder as a teacher, then those tools there will help you a lot in being able to understand what the code does. It's got solution or sample code in it, all kinds of neat resources.
Can we take a quick look at a lesson plan?
Yeah, let's do it. So every activity has a lesson plan. When we open the PDF, you'll see an overview. There's a real world connection. So we talked about those assistive robots, domestic robots, safety and security robots. So that's that real world overview. The learning objectives are listed. Coding concepts that are going to be covered are listed. There's a pacing guide to help you know how much time students should be spending on each task. So every activity is 90 minutes, and that's broken down to 45 minutes for the virtual part. Then if you're going to do the physical part, 45 minutes for using the physical robot. So that's how the activities are broken down. Also, we're going to walk you through task by task what students should be doing. So there's a goal to achieve. There are teaching points that are presented along the way. There are the solution code is provided. So we're right at the beginning here of just learning to code. So the solution code is pretty simple here. It'll get more complex as we work through different activities and tasks. But then there's discussion questions, and you can use these discussion questions however you want in your classroom. If you want to have a class discussion, if you want to have students discuss in small groups, you could assign them as homework for like an essay, research, all kinds of different ways. And those discussion questions, as Steph mentioned earlier, they turn it around all kinds of topics. Ethics, it might be how you might use what you've learned, the concept, how you might apply this robot in a different way, all kinds of different, how it impacts society, all kinds of different topics for discussion there.
Great. So now that we've seen the teacher side of it, can we jump in and look at what the students will be working through?
Yep, let's do that. So we will jump back over here, and I'm going to go to courses. And so students will have access. This is what a student's ought to look like. And it's important to note that when you're looking at a course as a teacher and when a student's looking at a course, it's exactly the same. So we're going to jump into, you can see here my 3 different units: assistive robots, domestic robots, safety and security. So we're going to jump into domestic robots because I like to walk the dog. That's my favorite activity. So activity 7 is that activity, and we'll go ahead and jump into that. And I'm going to jump into this part right here. So I've already had this loaded on a different tab. So we're in activity 7 here, and we are actually in task number 3. I can tell that from this window by it's where I am on the yellow. Now it shows here that I've already completed some of task number 4. I've actually backed up to task number 3. Remember, task 4 is that challenge activity. But we're backed up to task number 3 right here. So you can progress through the tasks. You can see your progression through the different tasks here on this screen. You can navigate back and forth through the tasks using these buttons up here at the top.
Gotcha. So I see you have some sample code loaded. Is that for every task?
Yeah, so this big area right here is our coding area. And so as students write their code, it saves their code when they complete it. And then every task, the subsequent task will start where they've left off. So this is where I've left off from the previous task. As they log out, log back in, the system will remember where they were, what task they were on, and it will log them into that task wherever they left off with.
So if I'm a student, how do I know how to progress through, and where do I find the instructions?
Yeah, so the instructions are given down here in this bubble that shows up down here, and you just navigate through the different instructions by clicking forward. You can always back up. If you need to, you can hide that bubble so you can see more of your code back behind there. From time to time, there might be graphics that pop up. So yeah, you just walk through the code until you get to the end. It tells you, okay, we're ready to run our code. So I've got my code here. This is our simulated environment over here. So let me zoom out a little bit. So using your mouse wheel, you can zoom in and out. So we've got kind of a virtual home. Remember, we're talking about domestic robots here. And so we've got an indoor and an outdoor part of our home. You can see our task bot. It looks just like this robot here on the sidewalk, and he's ready to walk the dog.
Great. So can we see the robot run?
Yeah, so we're going to go ahead. The instructions tell us to run code down there. So we'll click the run code button. And here we go. We don't actually have a dog in the environment, but that would slow the simulation down quite a bit. But you can see as the robot's moving, we can drag the environment around. And then once it completes its task, we get the pop-up, yay, we've completed the task. We wrote 13 lines of code. We can either replay the task and do it again if we want, maybe try a different solution. We can continue to the next task, or we can always X out of this window and just go right back and I can watch it again if I want to. I can reset the robot and play it again.
So students are getting immediate feedback as they are working through the task.
That's right. And if they fail for some reason, they'll get a pop-up box that says not quite, and that'll instruct them to go back, look at the instructions again, try to see, troubleshoot what they did wrong and debug their code that way.
Great. So we've tested it in the simulated environment and it works. So now we're ready to move it to the physical robot. Can you show us what that process looks like?
I can. And so we're going to take this code that we've written right here. And over here, I've got my, this is the name of my file, activity 7, task 3. I'm going to click this button and download my code. And that's going to download to my downloads folder. And then I'm going to share a different screen here. Okay, so we use the Arduino IDE for coding the physical robot. And so that's not only our coding environment, but that's also the software that we use to transfer code from the computer over to the Prism controller that's here on our robot. So I'm going to go ahead, I'm going to open my file. So I'm going to look in my downloads folder. I'm already there. There's my program that I just saved right there. When I open it, it's going to give me a message that it needs to be in a folder. That's just something that Arduino does. So I'll click OK, and here's my code.
So it's the exact code that the students worked on in the simulated environment.
It is. It looks exactly the same. The color coding is just a little bit different. That's because of the dark theme and the TVR environment. I've got the white theme going here.
Okay.
All right, so I'm ready. I'm going to plug in my USB cord to my robot, and we'll turn him on here. Once he comes on, then I'll just make sure that we're connected to the right port. And right here, I've got my upload button. I'll upload that. I can tell my code is uploading when I get the yellow lights flashing here on my robot. So it compiles the code. It's compiling right now. There it goes. So it's uploading. There's my yellow lights flashing. First time it always takes just a little bit longer to compile. Done uploading is what the IDE says. So now I can unplug my robot. And if I push my green start button, there my robot goes. He's walking the dog to the mailbox.
Nice. Very cool. Very cool. So now that we've seen the platform, how the students work through it, what the teacher resources look like, how we move the code to the robot, what's your top? You talked a little bit about the implementation support that's in TVR. So what's your top three ways that you like to see TETRIX virtual robotics in the classroom?
Yeah, so the first way to do it would be to do all of the digital lessons first. And then, so you work through all 15 activities. Well, there's actually 14, because remember that activity 6 is building the robot. So there's no digital activity there. So working through those lessons first, individually on your own device as a student, that way every student gets a chance to code on their device and learn the code. And then from there, you go over to the physical part of it, and you work through those activities again collaboratively as a group with the robot. So you get the individual one-on-one time, make sure every student learns the foundations of coding, and then you move to the collaborative part of building the robot and testing the code. An alternate way to do that would be to alternate back and forth between the digital experience and the physical experience. So you do activity 1 digitally, you come over, you do activity 1 physically. And that's probably my favorite way to do it, because you're taking what you've learned digitally in the simulated environment, then you're applying it directly, almost immediately on the physical environment. A third way to do it would be to split the classroom in half. And so you can have half the classroom doing the digital content while the other half of the classroom does the physical content. Then you can swap after they've gone through you can swap at any point, whether it's after a unit or after all 15 lessons, at any point that you want to do that. The benefit there is you need half as much equipment. So classrooms that don't have enough sets for the number of students that you have in your classroom, or maybe you're trying to keep your collaborative groups smaller for the physical, then that's one way you can do that, because you've only got half your class using the hardware.
Gotcha. So we've talked about implementation in the classroom. Can TETRIX VR also be used outside of the classroom?
It can. And so It can be used in camps, summer camps, after school programs, at home if you're a homeschooler. Yeah, lots of different ways that it can be used outside of the classroom.
Great, thanks. So with that, we've had an opportunity to learn a little bit about TETRIX VR, see the platform from the student and teacher perspective. Now I think we're ready for any Q&A.
Yeah, so first of all, looking at the Q&A, it looks like we had the chat feature disabled for the webinar.
Oh.
That's our fault, sorry about that. But it looks like we do have a question here. From Allison. She says, so can you make any build and then use the code from the virtual environment? The answer to that is yes and no. You can make any build you want out of your set. We provide lots of different ways to build different robots, building instructions. Of course, the students can always engineer their own robot. The caveat to that is in the digital environment, you only have the one robot that looks like this. So it might not be exactly the same as what the students build themselves. Now, a lot of mobile robots work exactly the same way. And so it might not look the same, it might not work the same, but if you've got what we call a direct drive robot, where you've got one motor controlling each drive wheel, then the navigation is going to be very similar to what's in the simulated environment. Might not be exactly the same. It kind of depends on where your wheels are placed on the robot, but it should work pretty much the same. You can code anything you want in that digital environment, put the code onto the robot, and sorry, I'm losing my voice. And then watch it run on your physical robot, whatever robot you've built. So that's a good question. Great question, Allison. We have any other questions? Charles says we're using Chromebooks. Will that hinder us in any way? And the answer is no. One thing that's important about the simulation is it's not dependent on the processor speed of the device. That simulation, as it's downloading, that's really what the processor speed affects, is how long it takes to download the simulation. Once the once the environment is downloaded, then the simulation runs the same speed, and that's because we want it to mimic the physical robot.
And then if they're using the physical robot, they would use, and using a Chromebook, then they could use the web editor through the Arduino IDE.
That's right. So because you can't download software directly on the Chromebook, there is a web application software for the IDE that you would need to use. We've got instructions on how to do that. So
yes, great.
So Allison is talking about, she asked, what is the cost? You want to run through that?
Sure. So the cost of a single TVR license is $19.95, and that is for a year subscription for a seat. If you have multiple sections of robotics or your coding class happening, you have a first semester and second semester, you can use that license in both semesters. You just clear your classroom, create a new classroom, that seat opens up, and you can reuse that seat for the second semester.
All right. So it looks like, does anybody else have any other questions before we close off? We've got about 3 minutes left here before our time limit hits. So Allison says, so 2 classes is only $40?
So the $19.95 is per a single license per a seat. So you would need yeah,
per
exactly.
student.
Yes,
Yeah.
per student. Yes.
So it depends on how many students you have in your classrooms, how many classes or how many seats you would need.
Mm-hmm.
All right. Well, it looks like that's all the questions. So
Yes, so thank you again for joining us today. Our session has been recorded and the recording will be sent out to all registrants and attendees via email. Those who attended today's session live will receive their certificate of attendance via email as well. Also, if you'd like to learn more about TETRIX VR, you can visit our website at pitsco.com/virtual-robotics. Thank you again and hope you all have a great day.